Hello, this is the intro video for Lab 10, which is the first of our 3 circuit labs. These next 2 will use the same simulation, and then the last one uses a different one that's a Java simulation. So um, much like I'm about to do for labs 7 and 8, which have a Java applet, I'll record a intro video for those of you who can run the Java applet, and then also um, a non-narrated version where I'm going through the questions in the lab, and you'll see what those will look like soon because I'm going to at least record those for 7 and 8 probably today and get them up early in the week so that those of you who have been waiting for some sort of solution for labs 7 and 8 can get started on that. So as I mentioned, this one is dealing with circuits. Looks a little bit different because I'm working off of the PDF that I have on my computer, which is a little bit different. So I'm not going to show you word for word as I go through the lab what's on here because I made some minor modifications to the version that's in the Canvas course now, like taking out asking for graphs and rephrasing stuff because you can't. There are a couple of times where it asks you to draw things, and that's not something that you can do easily for this. So it says describe instead of draw, but those are minor details. Overall, the bulk of the lab is not really changed all that much. So before we get started, there is or are 2 questions down here at the end of the intro section, where the first one asks what happens for a fixed resistance with whether you have an increase or decrease in current when you change the potential difference. So the equation you want to look at for answering both of these questions is probably this form of that, V over R is equal to I. So the first question is basically saying if you keep R constant but increase V, what's going to happen to the current? And then the second question is saying if you keep V constant, so fixed potential difference, but you increase R, what happens to the current? So using this equation, you can just kind of figure that out and answer those questions, or you can even come back to it after you've done the lab, after you've seen the behavior of a resistor. So what we'll be using is the DC circuit construction kit lab. This is an HTML5 simulation, so I'm just going to be able to hit run, and it will run in the browser. We'll just go straight to the lab part. And the first thing it's going to ask you to do is connect up a circuit that has a battery and a light bulb, and then makes the light bulb actually light up. So I've got those 2 components that we need to get to work. So the first question basically just says sketch the configuration that worked on my version, but yours probably says describe the configuration that worked. And then how many points of connection does each circuit element have? So if I come back to my simulation here, you'll notice that the battery has 2 ends, which is pretty clear because anytime you mess with a battery, you've got the positive end and the negative end. The light bulb also has 2 points of connection. So everything that I put in here is always going to have 2 points of connection. To connect this up and get it running, I'm going to take one of these wires, which also has 2 points of connection, 1, 2, and I'm going to connect one into this end of the battery, and then I'm going to connect this down here, and now I've got this lit up and working. Now you can see the electrons are going through the circuit this way, and that is my current that's flowing through the circuit and causing the light bulb to light up. So this is one configuration. You can play around and see if you can get another one, or two or three, because the next question after this is to come up with 3 more configurations that work. And then you need to describe what conditions must be met so that you have a current flowing. Really, 5 should come after 4. So looking at this, what I've got here is my current is flowing. I can mess around with this and come up with a few more configurations, but I'm not going to worry about that. What I need to have for this to work is some source of potential difference. That's my battery. And then a complete path for the current to flow. As soon as I broke that connection there, I can't get the current to flow anymore because I've isolated my circuit from the source of potential difference. So you need a source of potential difference and then a complete path. Whether you have something like the light bulb in the path that does something interesting or not isn't really important. But because I could make a circuit with just the wires if I wanted to. So if I were to snip this out again and snip this out, there's no way I could connect this that would make current flow. At this point, there's no source of potential difference, so I'd be missing that current. Also, I could snip the bulb out of the circuit and show you that if I connect these wires in and connect them to each other, I do get current flowing. You'll notice it says that the animation speed limit is reached. Well, that's because the wires have no resistance. So technically, there's infinite current flowing right there, and that's a bit of a problem for the simulation, clearly. All right. So part B is our measuring part. And the first thing you're going to do is connect 2 batteries. So we'll compare 2 batteries versus 1. And then we will do some measurements. All right. So back to the simulation. I'm going to put 2 batteries in turn. I'm going to put wire. And this is showing more current versus 1 battery because these are moving faster, though that's hard to see. But the light bulb is brighter. So to get more current or more brightness out of a light bulb, we need more current. So putting 2 in, I've increased my flow. So what I'm going to go ahead and cut that one out and reconnect this so that you can see that the charges move slower and there are fewer light rays here. So then we're going to make measurements for the circuit. First thing we will measure are the battery voltages. So we're going to measure the voltage across each battery. I will mention here that when we are doing this, we want to just write the number. Don't worry about the sign. This voltmeter that we're going to use to make the measurement, it's technically calibrated so that the red side should be connected to the positive and the black side should be connected to the negative. So if I do this correctly, if I put this here, and this is my battery 1, I get 9 volts for that one. And then if I do the same on this one, I get 9 volts for this one. But if I connected it the other way around, I get minus 9 volts. All that means is that the voltage is reversed from what the voltmeter is expecting to see. So I'm just going to go ahead and even if you see -9 when you do this, just record 9 or whatever your voltage happens to be. So each battery measured 9 volts. Then the series combination is across both of the batteries together. So negative at one end of one battery, positive at the other end of the other battery, and then it's 18 volts there. So the next few questions just ask about those numbers. So did the potential difference of the series, how did it compare to each battery? So this is saying, how does the number in 10 compare to either battery 1 or battery 2, not the sum of them? How does the sum of the two potential differences compare to the series combination? So here you're comparing 10 to the sum of your two battery voltages that you got in 9. Was the current greater when you had more or less potential difference? And what does that suggest about the relationship between potential difference and current? So this next part, we are going to change the potential difference of the battery. And when we say the battery, we're going back to one battery for this. So I'm going to go ahead and keep the voltmeter here, though technically you really don't need it for this part. I'm going to go ahead and just select this battery and trash it, and then move this over so that I have a complete circuit. Going to go ahead and keep this here so I can measure the voltage. And then there are 2 ammeters that you can use for this experiment. I'll show you how to use both. The easier one to use is this one, which is simulating a non-contact ammeter. For this one, all you need to do is put the crosshair over the wire that you're interested in. In this case, this is going to read that current directly. This is the simpler way if you just want to keep it simple and get through it quickly. The other way you can do this is by using a traditional ammeter. And this one is complicated in that we need to break the circuit to put this in. This non-contact one, I just have to hover over it, and they do make ammeters like this. For this one, what I'm going to need to do is to break my circuit. So I'm going to move this guy out of the way and insert my ammeter somewhere in the circuit, and then I can measure the current that way. Again, I'm going to go ahead and keep this on the battery going forward. I'm going to go ahead and leave both of them on so you can see that you get the same number anytime I do anything here as I go through the experiment. So the first thing it asks you to do is actually put the ammeter in and record the reading off the ammeter. And you can see that when I do this right now, each of them are reading 0.9 amps. So units of voltage are volts, units of current are amperes, which are amps. Units of resistance are volts over amps, which have a name of ohms, OHM, or the omega symbol. So like if I turn the values on here, that 10 ohms, this ohm is my unit of resistance. All right. So first table, we are going to go ahead and change our battery voltage to 5 volts. So I'm going to change this to 5 volts. You can't type in this version, so I'm just going to change this down to 5 volts. And then in the table, you're going to be recording the current and the voltage. So current here off of either one of my ammeters and my voltage. Then I'll increase this to 10 volts and record the current and the voltage. increase to 15. Same thing. So you just keep going up by 5 volts until you've got the table filled in. So this would be 5, 10, 15, 20, and 25. Or sorry, 5, 10, 15, 20, and 25, and then you record the currents there. So you talk about how the current changes when you increase the potential difference. I don't remember if I left this question in about the relationship, but it's pretty clear. So this one, second table is the exact same thing we just did for the light bulb, but we're going to change its resistance first. So I click on it, not right click. If you right click, I don't think it does. Yeah, it doesn't do anything in the browser. So click on this, go ahead and turn it up to 20 ohms. Put my battery back down to 5 volts and record the current. Increase to 10 volts, record the current, and so on until you fill in the table again. So you're going to be comparing your results here to the previous table. Your potential difference column is going to be exactly the same, but your current column should be different. There will be a similar behavior. If you notice, my current was going up as my voltage went up there. My current is still going to go up as the voltage goes up here, but probably by not quite as much. All right, so the data analysis in your version of the report has been watered down because I decided I didn't want to worry about graphs since you're not going to be able to turn in paper copies. So all you really are going to do with the data analysis is, I think it starts here with the slope of the line. So you'll take your first and last data point from each table and use that value to calculate the slope and put that in here. When you are calculating the slope, the voltage should be in the numerator and the current should be in the denominator. So you'll calculate both of these values. You'll compare it to the resistance. Remember, the resistance for bulb 1 is 10 ohms and the resistance for bulb 2 is 20 ohms. And I don't remember if I left this question in either. I should have pulled the updated version, but I didn't. So that's about it. I'm pretty sure I simplified the data analysis quite a bit. Graphs are not required for this report. So all you have to do is fill in the tables, use the table values to calculate the slope, and then compare that slope to the resistance of the light bulb in each case. So for table 1, did you get close to 10 ohms? For table 2, did you get close to 20 ohms? And that's basically it at this point. This one is relatively quick again, and you should be able to go through it pretty quickly. No one should have any problem running it. Any modern browser should be able to get this running without any sort of issue. And so next week's, we're using the exact same tool. You're just doing different stuff with it. So if you want to look ahead to Lab 11 and try to work on it yourself, it's just a little bit different. This lab focused on just the relationship between voltage, current, and resistance. The next lab is looking at what happens when we start putting more than one resistor in a circuit, either in series, head to tail, or in parallel where the heads and tails are connected together, and how they behave differently. So that's where we're going next. And then after that, we have our induction stuff, which is more in line with what microphones and loudspeakers deal with when we get to that part. So that's it. And hopefully this helps. And good luck with this lab.